So the last part of this topic on Lagrange multipliers will be the Kuhn-Tucker conditions, the KTCs, okay, which help us extend the concept of Lagrangian, the method of Lagrangian multipliers even to problems involving inequality constraints. Basically this Lagrange multiplier method so we are actually doing it is analogous to defining a function L which is y minus lambda phi and we are trying to make it stationary, okay. Then you will get you can just solve for del you could solve for del L equal to 0 and then you will get all the answers in terms of lambda, and technically it is possible for you to adjust the value of to fine tune the value of lambda such that you get realistic solutions. But because we do not want to do that exercise, apart from making del L equal to del of L equal to 0, we also add phi equal to 0 and solve the n plus m resultant equations to get m Lagrange multipliers and n values of x1 to xn, right. So this L is called the Lagrangian function. So some people like Ravindran and Reclitis, they will say that this is analogous to converting the constrained optimization problem into an unconstrained one, though I do not fully agree with this because the constraint is still hanging around there, okay. First they are saying that once you put this lambda del phi, you made this you incorporated the constraint, but still this alone if you solve you will get all the answers in terms of lambda, okay. You have to actually use an additional equation phi equal to 0 for one constraint problem to get the value of lambda also apart from the other things, right. So this is in so far as, so L one other concept, yet another concept is we are actually trying to solve for the Lagrangian function, where the Lagrangian function is basically y minus lambda of phi. This is basically, right, this is one way of looking at it. Operations research people will look at it this way. If you look at any OR book, when they talk about Lagrangian multiplier, they will introduce the Lagrangian function or Lagrange function first, okay. Now how about handling inequality constraints? The simplest approach would be to ignore the inequality constraint and solve the problem. Ignore the inequality constraint and solve the problem with equality constraints, and the resulting solution you find out whether it violates the inequality constraint or not. If it does not violate, then it is no longer an active or a binding constraint. If it violates, then convert the inequality constraint into an equality constraint and put it as an additional constraint in your Lagrangian multiplier formulation and solve it, and then anyway that constraint will be obeyed by the solution which you eventually obtain, right. So if had we known this information in advance, if we had known which are these constraints which are active or binding, there is no need for us to go through this exercise. In advance we would have made some inequality directly into equality and then completed a solution, but there is no way a priori or upfront you will know you know whether a particular constraint is active or binding, okay. So this problem was thought about by Kuhn and Tucker, and then they finally came out with the process of mathematics at Princeton University. So they came out with these Kuhn-Tucker conditions, okay. So KTC or KTCs. Before going into what these Kuhn-Tucker conditions are, something from a point of view of history. Professor Tucker is no longer alive. He was the PhD advisor of John Nash. John Nash, who won the PhD for economics in 1994, who was the subject of this movie A Beautiful Mind, okay. So he was the advisor of John Nash. Then Kuhn was a contemporary of John Nash. Kuhn is a contemporary of John, he is still alive, and Kuhn continues to work in Princeton University. He was a mathematics consultant for that movie, right. He was largely responsible for them making this movie, and also largely responsible for nominating Nash for the Nobel Prize. These two guys have done lot of work on operations research, and Tucker has worked on basically game theory, and there is something called a prisoner's dilemma, right. Some of you are, I cannot go deep in, there is a prisoner's dilemma. Two fellows are caught, they are kept in separate cells, they have to now vouch. If both of them keep quiet, they will get minimum sentence, but if they RG, they will get more sentence. And then one fellow, so what should they do? I mean, what should they do? That people have come out with lots of these things, and lots of papers have been written. That is a prisoner's dilemma. Tucker has worked a lot on this prisoner's dilemma and so on. Okay, that is the historical perspective. But what are these Kuhn-Tucker conditions? So we have to now formulate the optimization problem with inequality constraints also. Consider they also developed the Hungarian method for the assignment problem. There are various problems, the transportation problem, traveling salesman problem. That is what is called the beaten to death problem. Everybody will, just like my cylindrical water storage, which I will beat to death by the time we are done with the course. So assignment problem, transportation problem, northwest corner rule. You start from the northwest. Why can't you start from southeast? That looks like the same answer. What is this northwest? What is so great about northwest? You can start from any corner. Anyway, they call it as a northwest corner rule and all that. So he has worked on the Hungarian method assignment problem. So consider y equal to x1 to xn subject to okay, and greater than equal to 0. All these fellows are now starting up to psi r. Where psi's are the inequality constraints. I am writing this for a minimization problem, minimize. Okay, we can have an analogous formulation for the maximization problem also. Why minimization greater than equal to constraint is there? For the furniture company making tables and chairs and or something, if you want to minimize the cost, you do not make anything at all. I mean, but that is a very trivial solution. So these greater than equal to constraints ensure that entropy is greater than 0 and some activity is generated. Okay, so if entropy has to be 0, everything has to come to a standstill. Okay, subject to, now we have to write the KTCs applicable to this problem. Okay, now it involves some tricky less than equal to greater than equal to. So we will go through this very carefully. Okay. So it is analogous to, so this is the Lagrangian function which you want to minimize. Okay. Please note that up to this portion it is the same as the Lagrange multiplier method. Okay. I have handled the objective function y, I have handled all the constraints, equality constraints for which phi equal to 0 and it is applicable for I equal to 1 to n, right. Now I put one more minus r equal to 1 to k. Okay, what did I do? Already there is a I will make it k here. I thought about all these things j, m, k, something we have to, alright. So, I put k, I put r, r is equal to 1 to k u r psi r, where psi r basically represents the inequality constraint and u is something which is similar to the Lagrange multiplier. It is a sensitivity coefficient whose nature is not yet unknown, no, nature is not yet known for us, right. Now, we have to write the, we can call this as equation 1, then phi is equal to 0 for all yeah correct for all phi I equal to 0 for all I, that is I equal to 1 to m, then psi r is greater than or equal to 0 for all r. So, I will put it as 2, I will put it as 3.
Is that lambda I del phi I or lambda I?
Yeah, what is that? Yeah, lambda I. Yeah. Now comes the new conditions, right. Up to this there is no problem, right, except that we got something extra in terms of psi, which is an inequality constraint, but so far there is nothing which is new to you, but now we will introduce some new things. Basically u r psi r is equal to 0 for all r, and u r is greater than or equal to 0 for all r. Do not worry, I will explain all this. Okay. For a maximization problem, the minus of y has to be minimized. If you want a maximum of y, you can do minus of y, that has to be minimized. This is a very important condition introduced by Kuhn and Tucker. Okay. This 4 means either psi equal to 0 or u equal to 0 or both are 0. I come again, so it is a very important condition, either psi is 0 or u is 0 or both are 0. If u is equal to 0, there is no problem at all. U is the sensitivity of your objective function with respect to that constraint. If u is equal to 0, we are home. It is no longer an active or binding constraint because it no longer affects the solution if u is equal to 0. Okay. We are worried about those cases where u is not 0. If psi is equal to 0, then it is a problem because it is an equality constraint, it is strict condition, equal to is a strict condition. Okay. So, there is a complementarity involved in this, either this or this. So, this is called the complementary slackness condition. What?
The sigma on the object is equal to 0.
A priori you do not know whether psi has to be considered or not. So, Kuhn and Tucker evolved some conditions where it after going through one iteration it let you know whether it is binding or not. After we go through the example it will become very clear. Okay. U's are very similar to lambdas. Watch very carefully, U's are very similar to lambdas except that they are not unrestricted in sign. Lambdas are unrestricted in sign, lambda can be 0, lambda can be negative or lambda can be positive. It is possible for you to have an increase in the objective function with an increase in the constraint or decrease in the constraint or no change in the objective function. However, the u's are restricted in sign, the u can at best be 0 or it has to be more than 0 because it accompanies an inequality constraint, it does not accompany an equality constraint. Okay. So, now let us consider a 3 variable one equality constraint, one inequality constraint optimization problem. I will give an example, it will become clear. That means there is one psi and one phi. I have made
Inequality constraint.
huh?
Inequality constraint should also have a gradient.
Sorry, sir.
So he's saying there will be a UR into del psi r.
Be UR del psi.
Yeah. Yeah. I thought you were talking about the other thing. Okay. Now, if you consider 3 variable 2 constraint problem in which one is an equality constraint, one is an inequality constraint, if psi is active, equation 3 becomes an equality. And you may take on a positive value. This is basically the KTC, right? Okay. So, I come back to the same point again. If you want to handle Lagrange multiplier, if you want to use Lagrange multiplier method for a problem with m constraints and which are non-linear but which are differentiable, it is possible for you to completely ignore the inequality constraint and proceed with the solution and see whether it is violated or not. If it is violated, then you have to reinsert the inequality as an equality and proceed. Next time it will be obeyed. Alternatively, you can use the KTC condition, assume that a particular inequality constraint is active, solve the resulting set of equations. Apart from lambda, you will also get u. Look at the nature of the u. If u is negative, your original assumption that psi is active is wrong. Therefore, that can be omitted from the calculation in the next iteration. How many of you didn't follow this? Okay. The funda behind the KTC is like this. When you start with the solution, if you want to take a particular, if you want to assume that a particular psi is active, you just go ahead and assume that a particular psi is active and treat it. If it's active means you treat the inequality as an equality. Then come out with all the come out with the complete solution. There may be other equality constraints in the problem, but this inequality is also treated as an equality. So for this psi, you have an appropriate u, which will be u1, u2, u3, whatever. If it is only one psi, let us assume that there is only one psi, you get a value of u at the end of the solution. If u is positive, then it means it is binding. U is positive, it is binding, okay, because then when psi is increasing, the y is also increasing, you are seeking a minimum to the problem. Therefore, it is binding, and what you have done is correct. If you assume psi is active, you have proceeded with the solution, u is negative, then your assumption that this is an active constraint is incorrect. So it is telling you from the next iteration onwards, you can drop this constraint and proceed. This is the KTC. In any case, in either case, you are RG'd. In either case, it is an iterative process. You do not know. You have to do iterations and find out whether a particular constraint is active or inactive. Okay. So we will demystify the Kuhn-Tucker conditions with examples. Okay. Let us Problem number 30, yeah? Problem number 30, okay. Consider establish KTCs for the problem given below. Min, it is the same circle problem, right, where y are iso-objective lines are basically square of the radii. Now I have given an additional constraint x1 plus x2 must be greater than 9. So we want, this is an inequality constraint, so we want to use the KTC. The first step in technology is assume that it is an active constraint and see whether u is positive or negative. Can you do this? Pretty straightforward, okay. Then I will draw x1 x2, I will draw iso-objective lines and I will graphically we will see whether it is binding or not. It is a straightforward problem, right. What is your guess? What is the solution? 8 and 6, x1 plus x2 is greater than 9, is below the solution or above the solution? I mean to the right, it is below and to the left of the solution, it should not affect, you just see. In this case it is obvious, so you feel the KTC is not required. In many cases it is not so obvious, therefore the KTC is extremely helpful, okay. Let me draw the solution on the depict the solution graphically. Let us start with the KTC for this. Dou y okay. Now assuming psi is active, correct, this will be equation 3. Then u into psi equal to 0, u greater than equal to 0. These are the 5 equations, 5. So this gives you the KTCs. Now solve. Now solution. So what is the solution? 2 x1, that is all, right, equal to 0. Am I doing all right? Am I doing all right? Sampath? Fine. What is u? U is minus? Totally wrong. U cannot be negative. That is a KTC. Therefore, your original assumption that the psi is an active constraint is incorrect. Therefore, psi does not affect the solution to this problem. Okay, this is also graphically beautifully seen. Okay, so the center point is y equal to 0. Where is this fellow x1 plus x2 is equal to 9? Is here, right? Okay, somewhere. So you are talking about this region. When it cuts, you get some other solution. You get this solution for which y is equal to 4 or something. How much is the value of y? How much is the value of y for this? 6.25 plus 6.25 plus 6.25 12.5. I have a solution for which y equal to 0, which does not violate x1 plus x2 greater than 9. So it is absolutely wrong. So the KTC has helped me identify that by putting x1 plus x2 is equal to 9 as an active constraint, I made a major mistake. Alright, let us look at it. Is it clear to everybody now? How many of you still have issues with KTC? Hurry, okay. Now let's rework the problem for x1 plus x2 greater than 18. U comes out to be 0, but psi equal to 0, E equal to 0.
By the other condition, U or psi are equal to.
If U is equal to 0, it is not at all an active or a binding constraint. There is no sensitivity of the objective function. There is nothing more you can talk about it. If U is 0, it means Lagrange multiplier is 0, means what are you saying? See, some people call the U also as Lagrange multiplier, because when you actually find the value of U, you are treating it as an equality. So strictly it is also a Lagrange multiplier. If U is equal to 0, there is nothing, it doesn't cause any disturbance to the objective function. Now please rework the problem, all the other things are pretty straightforward. Up to this the steps are the same, right? Abhishek, you got it? You got the idea of the whole thing. Now this will be so evident. I think what you should do, if you are smart, what you should do is, for 31 you should assume that it is not active and get a solution and then prove that you made a mistake, therefore you have to consider, that is alright. Otherwise take it as binding and you will get a value of U which is positive, that means your original assumption is correct, fine. Now let us do this. So psi, then psi U into psi is correct, x2 8. Now I think we have to redraw this. So if x1 is, so you get x1 equal to 10 plus 4. That is the logic. So Kuhn and Tucker, they nicely put common sense in a formal mathematical way and then establish this. So we have this 8 6 right here. So this is somewhere it cuts 12 1 10 okay somewhere. So now the two approaches, you can alternatively you can disregard the constraint and find out whether it, if you disregard the constraint, what is the solution you are getting? 8 and 6. If you substitute 8 and 6, this will violate that constraint. Okay. If you and then what is the value of u you will get? No, if you do not consider the constraint, minus. Okay. Therefore it is incorrect. Therefore your assumption that the constraint is not binding is not correct then. You did not catch the point. There is one more way of doing it. What I am saying is, if you disregard the constraint, you get the solution 8 6. Proceeding with 8 6, if you try to calculate the u and other things, the u will give, it will lead to a negative answer u, which is again incorrect, right. Therefore for that, since u is negative, what is incorrect? Your assumption that the constraint is not binding. Okay. Now before closing this discussion, so there are two approaches to solving there are two approaches to handling inequality constraint. Number one, ignore the constraint, see whether it is violated. Now you ignore the constraint, you get the solution as 8 and 6. 8 and 6, if you substitute here x1 plus x2 greater than 18, it is violated. Therefore the constraint is absolutely violated if you ignore, therefore you made a mistake by not considering the constraint. This is a very crude way of handling this. The second is formally apply the KTC, treat it as an active or a binding constraint, take psi equal to 0 and get the value of u. If the value of u is positive, your assumption that it is an active or binding constraint is indeed correct, and in the next iteration, subsequent iterations, if your problem involves many iterations, you have to treat it as an active constraint, replace the inequality by inequality. If on the other hand it is not binding, you can omit that constraint from the problem. For example, x1 plus x2 greater than 9, there is no need for you to consider that in subsequent iterations. Okay. One last point and then we will close.
How do we find the new value?
What new value?
Then when this constraint is applied, 8 and 6 will not be the solution.
Yeah, it is not the solution. Yeah.
Assuming that it is.
No, I don't get your point.
When we are considering
But we got the new solution 10 and 8, what is the problem? We got the new solution 10 and 8. If you assume this to be, they are constrained to be inactive, you will get 8 and 6. but 8 and 6 is will violate the constraint x1 plus x2 must be greater than 18, therefore it is wrong. So you cannot live with that 8 and 6 for this problem. No, huh? Each of the u's you have to find, each of the u's have to be positive. Everything, all the u's have to be positive.
So 2 raised to 2 power n. We may have to check 2 power n.
Yeah, your computer will check, right? Computers do how many million floating point operation per second. You don't have to do it in the classroom. Okay, so one last point. Conceptually, why should you be positive? all this discussion hinges on the assumption that while the Lagrange multiplier lambda is unrestricted in sign, the u is restricted. Why are we partial to this lambda and why do we RG this u? It is very simple. U is also delta correct. It is a sensitivity of the objective function with respect to the particular constraint. Watch, I am not using del phi, I am doing del c, del psi, right, because u corresponds to the inequality constraint, right. Let psi be greater than or equal to 0, solve, we get a feasible solution. Okay. Now, what does it mean? Now I make psi greater than or equal to 1 and solve the problem again. So what I have done is I have essentially made del psi positive. When I have done that, the feasible region is reduced. Any solution which satisfies psi greater than or equal to 1 will automatically satisfy psi greater than or equal to 0, but the converse need not be true. Any solution which satisfies psi greater than or equal to 1 will satisfy psi greater than or equal to 0, but now I have a reduced feasible region. There is no chance for my y to improve. At best it can be in this portion of the curve. I can't expect y to improve, y can be the same or y can only decrease. Therefore, while psi increases, y has to necessarily increase for a minimization problem. Therefore, if del psi is positive, del y is also positive. I cannot hope to get a new value of psi which will be less than what I got when psi is greater than or equal to 0 when I apply psi greater than or equal to 1. Therefore, use positive. Okay, it's just plain common sense.
What will be the changes in maximization term?
Huh?
What will be the
No, generally we define it for minimization. Instead of putting words in my mouth, I will say treat minus of y and consider it as a minimization problem. That is it. Okay. Are we through? Right. So this closes our discussion on Lagrange multiplier. From the next class onwards, we will start our journey of search methods. Okay. Thank you.